Hey everybody, this is a Unit 9 test commercial. Let's look at some of the topics that were covered in Unit 9. So we had separable equations, differential equations like real scenarios. We had slope fields, we drew them, we did matching, and we drew particular solutions through slope fields. And we talked about critical points, inflection points, and concavity. So let's look at an example of a separable equation that is an exponential form. So remember, anytime you have a derivative on the left and a constant of proportionality, and if you are directly proportional to the main variable, in this case which is p, okay, we can just jump right ahead and write the final answer, which is c e to the k t. And I guess technically my y variable should be p in this case. Okay, so how do we get that? Let's just review really quick. We're going to separate the variables. dp over p equals k dt. A common error is moving the k into the denominator with the p down here. It's probably better to just leave it on the right hand side. Okay, so we're going to take the antiderivative, both sides, and on this side we're going to get ln absolute value of p equals kt plus c. And now we're going to solve for p, so I'm going to say p equals e to the kt plus c. And remember, we can rewrite this as e to the kt, e to the c, and this right here becomes a constant out in front, which is c e to the kt. Okay? Let's look at an example that is non-exponential. So here we have to separate the variables again. So I'm going to move the y down here and move the dx up to the top. So I'll have dx over cosine squared x. Okay, and then we're going to integrate both sides. So if we integrate the left, we're going to have ln absolute value of y. And what do we do with this side? Yuck. Okay. So here we have to use some trig tricks. Let's just remember that if we had 1 over cosine squared, that's really secant squared. Okay. Now we can integrate the right. So we're going to get ln absolute value of y equals tan x plus c. And we're going to solve for y. We'll have y equals e to the tan x plus c. And just like in the previous example, we can move that c to the front. So we'll have c e to the tan x. Okay. We had differential equation scenarios. So here's an example. The instantaneous rate of change of a bacteria population is directly proportional to the population itself. And in these problems, what we have to do is write the differential equation first. So I'm going to use the letter b to represent the bacteria population. And I'm going to have dB dt represent the growth rate of, represent the instantaneous rate of change of the population. And we're saying that's directly proportional to the population itself. Okay, so that direct proportion translates into this KB right here. Okay, anytime you have a direct proportion to a concept itself, you use this kind of formula. Okay, and remember we can solve that, and we're going to get B equals C e to the KT. Just watch for the wording in the problems. Let's say it said something like inversely proportional. Okay. Proportional. So if the population was if the instantaneous rate of change was inversely proportional to the population itself, we would have dB dt equals k over b. Okay. We made slope fields, so let's just review how to do that. If I have dy dx equals x, that means my slope field, my differential equation, is x. So what I'm going to do is I'm just going to start making points. So we'll say point and slope. Okay, so at my point 0, 0, I'm just going to take the x-coordinate. So my slope would be 0. Okay, at my point 1, 1, take the x value again, so my slope would be 1. Okay, at 2, 1, my slope would be 2. So I'm going to draw that a little steeper. Okay, whoops, sorry, that's an error. That would be 2, 1, that would be out here, so my slope would be a little steeper over here. And then we can just fill in the table. So this is an easy case because whatever the x value is, I have the slope. So right here I'd have 0, 0, 0, 0, 1, 1, 1, okay, 2. Okay, on the left side I would have -1. And there you go. And let's say I wanted a particular solution. Let's say I want the particular solution, okay, solution through, let's say 0, -1. So through 0, -1. Okay, I'm just going to go with the flow and follow the slope field, and voila. Okay, let's say you're given the slope field and you want to write a differential equation to possibly represent this. Okay, so the first thing I'm going to do is I'm going to draw a particular solution. Okay, ooh, what does that curve look like? Okay, get a little more flat right here. Okay, it looks like we have the equation y equals x cubed. Okay, and it's really easy to fall into the trap and say that x cubed is the differential equation. Okay, but it's not, because the slope field represents the solutions to the differential equation, which are like the antiderivatives, the family of curves. So I have a bunch of x cubed curves right here. So you can think my antideriv is x cubed plus c. Okay, so what's the derivative of that? Okay, so my derivative would be 3x squared. Okay, and so this would be a possible solution to represent this slope field right here. Okay, finally we have critical points, max mins, and inflection points. So let's start trying to find the critical points here. We're going to take the derivative, and we're going to look for where it's either 0 or undefined. Okay, so if I take the derivative here, I'm going to get 4x to the cubed over 4, which gives me x cubed, plus 3x squared over 3, which is x squared, minus 2x. I can go ahead and factor out an x. So I'm going to have x times x squared plus x minus 2. Okay. I can factor that further. Okay, so I got x times x plus 2 times x minus 1. And that's our f prime of x. So we're going to set that equal to 0. And so we have x equals 0, x equals -2, and x equals 1. Okay, so those are our 3 critical points. Okay, let's go ahead and make a number line here. 0, let's see, -2, and 1. And we're going to test within each region to determine the behavior of f of x. I'm just going to make this a little longer. Okay, so if I pick a number to the left, all we care about is the sign of what's happening to each piece. So I'm going to pick a number, let's say -100. The x, okay, the x right here would be negative. The middle term, the x plus 2 term, would also be negative. And the right term would also be negative. So I got negative, negative, negative. That means this whole region is negative. Okay. I'm going to pick a number in between negative 2 and 0, so let's pick negative 1. Okay, the x would be negative. The middle term would be positive. And the right term would be negative. So this whole term in here is positive. The whole section of the graph is positive. Let's go between 0 and 1. Let's pick 1/2. So the x term would be positive. The middle would be positive. And this would be negative. The x minus 1 would be negative. So I'd have positive times negative. This would be negative. And finally, picking a number to the right, I would have positive for x, positive, positive. So this whole section is positive. Okay, so what does it mean if the derivative is positive? Those are the intervals where f is increasing. Okay, so f increases on the positive intervals and f decreases on the negative intervals. So from here we can determine if we have maxima or minima. Okay, it looks like since we change from negative to positive, we have a minima at 2. Okay, we change from positive to negative at 0, so we have a max. And negative to positive again at 1, so we have a min right here. All right, let's go ahead and take the second derivative. So we're going to have f double prime of x equals 3x squared plus 2x minus 2. Okay? 3x squared plus 2x minus 2. And what we would have to do is we would have to set this equal to 0 to find out if we have possible candidates for inflection points. Okay? And then we're going to take those values that we get and put them on a number line. Okay? I'm not going to solve this quadratic right now. I'm going to leave that to you to do as an exercise. But the big thing is, when we put the numbers on the number line, we need a sign change. Okay, we need a sign change to prove that we have an inflection point. Okay, so let's say I have a number line. Let's say this is my second derivative. And let's say I get plus and plus. And let's say this is my candidate point. Okay, that means this point right here is not an inflection. Okay, not an inflection on f. Okay, but if I had my candidate point for an inflection and it was plus to the left, minus to the right, or if it was minus and plus, okay, then this point right here is an inflection point on the graph of f. Okay, last thing to be aware of is the intervals of concavity, right? If I have a scenario like this above, and I have positive, positive, that means f is concave up. Concave up on those positive intervals. Okay, if I have a scenario like one below, where I have minus plus, f will be concave down on this interval and concave up on this interval. Okay, that's the test commercial. Good luck. Study. You guys will do great.